Good evening, everyone. I'm going to be giving a seminar on the topic stereoisomerism, and this topic is under Unit 1 in Pharmaceutical Organic Chemistry 3, fourth sem B Farm. So, under this topic, we're going to be talking about few subtopics, which include the introduction to stereoisomerism, the talk about optical isomerism, we'll talk about optical activity, enantiomerism, diastereoisomerism, mesocompounds. We'll talk about elements of symmetry, chiral and achiral molecules. Then let's get started. So basically, before you talk about stereoisomerism, you have to understand the meaning of isomers. So basically, in organic chemistry, isomers are molecules with the same molecular formula, as you all know, but different structural or spatial arrangement. Now, if you're talking about different structural arrangement, then you have to be talking about structural isomerism. But if you're talking about spatial arrangement between the atoms around the carbon in space, then you're talking about stereoisomerism. In the next slide, I will show you the different types of isomerism. Then you can see here isomers. They are classified into structural isomers and stereoisomers. So structural isomers can also be called constitutional isomers. And under that, you have some subclass, which include chain isomerism, positional isomerism, meta isomerism, ring isomerism, then tautomerism isomerism. I'm not going to explain this structural isomerism because I think we did it in our POC one, so I think it's still fresh in our minds. So I'll just go straight to stereoisomerism. So basically, under stereoisomerism, we have conformational and configurational. Now, conformational means like stereoisomers having different relative positions of atom within the molecules and which can be interconverted by simple rotation. This and we should note that in conformational isomers, they don't require breaking and remaking to remove the covalent bond. But for configurational, it requires the interconversion requires breaking and remaking of covalent bonds. So this is just the major difference between conformational and configurational isomers. So now we're going to move to the subclass of configurational isomers, geometric and optical. So basically in this class, we'll be talking about the optical isomerism. So um, optical isomerism. What are optical isomerism? So basically, if you look at the slide, optical isomers are two compounds which contain the same number and kinds of molecules and kinds of atoms and bonds and different spatial arrangements of atoms, but which have non-superimposable mirror images. Oftentimes in this topic, you see something like superimposable, non-superimposable. So I'll just try to break it down to simpler English there. For something to be superimposable, it means um, it's forcing itself to something. For example, if you're looking at a mirror, for example, and you're standing straight with your right hand this side and your left hand the other side, in the mirror, it turns to be as if it's opposite what you're standing, like you're facing yourself opposite. So that you're not superimposing yourself to the mirror is giving you a slight change of yourself. So that is non-superimposable mirror image. For superimposable, it means for example, if you show A, the letter A on a mirror, you will still get A in the same mirror. You're not going to get something like upside down A or something. So that is superimposable. It's imposing its image to the mirror. So that is just the breakdown of that superimposable and non-superimposable. Because oftentimes in this topic, we are going to be seeing that. So I just want us to bear in mind that's how it works. So about optical isomerism, as you can see here, isomers which differ only in their behavior towards plane polarized light. That is, one isomer rotates the plane of polarized light towards the right side, that is dextro-rotatory, and the other one towards the left side, that is levo-rotatory. Such pair of isomers are called optical isomers, and the phenomenon is called optical activity. So sometimes people confuse themselves with what isomers are and what isomerism is, or what optical isomers are and what optical activity is. So activity means is activity is like the phenomenon, and isomers is like the thing itself. So basically, you can see for lactate, there's a mistake in the labeling. It's supposed to be um, L-lactate to the left side and dextrolactate to the right side. So basically, D is represented with plus and L is represented with minus. As you can see there, there's a mistake here. So just get it corrected with yourself. Um, in order for us to understand the phenomenon of optical activity, we must know the following terms, one of which is plane polarized light. Now, what are plane polarized light? We know that a normal ray of light has different magnitude, have different wavelengths, and the radiation vibrates in different planes of the same angles, of right angles. So you cannot use plane polarized light to know if something is optically active because it has different wavelengths and it vibrates in different directions. So basically, if you want to talk about optical activity, you have to talk about plane polarized light. Why? Because plane polarized light, they vibrate in only one direction. As you can see in the description here, light whose electric field oscillates in just one plane are called plane polarized light. So plane polarized light is defined as a beam of light having vibrations only in one plane. We should take note there, only in one plane, not like the normal rays. Then we should note that an ordinary ray of light consists of electromagnetic radiations of different wavelengths. These radiations vibrate in all planes at right angles to the direction in which it travels. But we cannot talk about plane polarized light without talking about nickel prisms. So nickel prisms are just like they're used to obtain plane polarized light. And these nickel prisms, they are called polarizers. In the next slide, I will show you the types of nickel prism you can use because basically nickel prisms consist of two two what do you call that? You need two nickel prisms for a polarimeter, which is the polarizer and the analyzer. I'll tell you about it in the next slide. Then the next thing you have to know about in this topic is optical activity. It's not optical, it's typo error. I'm sorry for that. So it's optical activity. Now, this was first discovered by the French chemist Louis Pasteur in 1848. Substances which can rotate the plane of polarized light through a certain angle are called optically active substances. And this property of a substance by virtue of which the organic substance rotates the plane polarized light is called optical activity. Now, the English is looking at like it's so big, I'll have to break it down. So it's just like if you're a cricketer and you play cricket, someone that plays cricket is called a cricketer. Same thing here. Someone like an optically active substance has optical activity. It exhibits optical activity. Same thing also. If you play cricket, you're a cricketer. Same thing here also. If you exhibit optically active, or yeah, if you exhibit optical activity, then you rotate the plane of polarized light. So that is just how it works here. So optical activity is just like that, and angle of rotation is another thing we have to note. Angle of rotation or specific rotation. This is the angle in degrees through which the plane polarized light is rotated by an optically active substance. The degrees should be 360 degrees. So the angle in degrees through which the plane polarized light is rotated by an optically active substance is called angle of rotation, and it is denoted by alpha symbol. And the instrument used for measuring the angle of rotation of plane polarized light is called polarimeter. I told you before that a polarimeter consists of two nickel prisms, one the polarizer and one the analyzer, a light source, usually sodium lamp, and a polarimeter tube. You can see in this image a polarizer, the sample compartment, and the analyzer. In this image, normally there's a light source. It's not shown in the image because of some issues. Then there's a light source. That light source is converted into a vibration in one plane by this polarizer, and then the sample compartment, this polarimeter in the middle of the polarizer and the analyzer is it should be in the middle because the analyzer should be at the end and the polarizer should be at the other end with something in the middle, which is a sample. As you can see here, this is now a textbook. You can see the source, the light source, then you can see the polarizer, the nickel prism polarizer, then you can see the plane polarized light in going in one direction. It has been converted to one direction. Then you can see when it passes through the polarimeter tube and passes through the analyzer, then it rotates. That is angle of rotation. It rotates towards one angle. As you can see the rotated light there. Next is the optical activity is expressed in terms of specific rotations. Now, we have to talk about specific rotation because we're talking about angle of rotation. So, specific rotation is defined as the degree of rotation of plane polarized light produced by an optically active compound of concentration 1 gram per ml present in a polarimeter tube of length 1 diameter at a specified temperature and wavelength. We have to note it should be at the compound must be of concentration 1 gram per ml present in a polarimeter tube. The polarimeter tube must be of length 1 diameter at a specified temperature and wavelength. So it is given as this. This is the formula for specific rotation. You can see alpha equals to the observed rotation in degrees, and the specific rotation is given as alpha over C multiplied by L. The C is concentration in grams per ml, and L is the path length. As I told you, it should be 1 diameter. The concentration, as you can see here, should be 1 gram per ml, and the length should be 1 diameter. So this is the formula for specific rotation, as you can see. Then move on to chirality of molecules. So in chemistry, a molecule or ion is called chiral if it cannot be superposed on its mirror image by any combination of rotations and translations. This geometric property is called chirality. So basically what this is trying to say is a substance that have four different when a carbon has four different groups of atoms attached to it, it exhibits chirality. It's called a chiral carbon. So basically the term is derived from ancient Greek meaning hand, which is a canonical example of an object with this property. I have to show you how it works. Then a molecule is chiral or disymmetric only if it's superimposable on its mirror image. In contrast, a molecule or an object which is superimposable on its mirror image is called achiral or symmetric compound. As you can see here, look at the hand. You can see the H on the right hand is the H on the left hand, as you can see there. So it's non-superimposable. As you can see there, there's a twist because basically your right hand and your left hand are not the same now. So you can see the H on the left hand side here move to the right hand side, and the R on the right hand side here move to the left hand side in that way. So this is just like it's non-superimposable. It's not imposing the exact image on that hand to the mirror. So you can see the difference there with your right hand and your left hand. Basically, it's one image, but it looks as if it's your right hand and your left hand because of the non-superimposable nature of it. So next is chiral and asymmetric carbon. An asymmetric carbon or carbon atom, chiral carbon, is a carbon atom that is attached to four different types of atoms or groups of atoms. Examples: lactic acid. You know, lactic acid have the CH group, the OH group, and the alcohol group also, the carboxylic group also. So the mirror image of such carbon is non-superimposable, as shown in the next slide. You can see the image here. You can see the carbon, the chiral center. You can see the groups attached to it. You can see the OH group. You can see the the methyl group. You can see the hydrogen. You can see bromine. There are four different atoms attached to one carbon. And in the mirror image, in the other side, you can see that these things are like non-superimposed. They change direction. That is just the summary. It changes direction when it reflects to the mirror. When it's seen on the mirror, it changes direction. That's what it means by it's non-superimposable. It doesn't remain the same when you see it in the mirror. It's not like this. So this is how it should be. Then elements of symmetry. So basically there are three elements of symmetry which helps in identifying the superimposability of a molecule and object, and it's a mirror image. Chiral objects do not have an element of symmetry, while achiral objects and molecules have one or more elements of symmetry. So you should take note that chiral objects they do not have any element of symmetry, and I will list the elements of symmetry for you. So the elements of symmetry we're talking about is the plane of symmetry, the center of symmetry, and axis of symmetry. We'll get to know what they mean. So the plane of symmetry, a plane of symmetry is an imaginary plane that bisect means that cuts in between a molecule into halves that are mirror images of each other. For example, you can see this compound. So plane of symmetry is like a plane, an imaginary plane that cuts from the middle of this carbon, the middle carbon, that divides the compound into two, having mirror images of each other. Like what you see in this place, the same thing you're going to see in the other place. Exactly the same thing. So that imaginary plane that cuts into two halves is called a plane of symmetry. For example, the vertical plane that bisects the methyl group and carbon atom and the hydrogen atom bisect the molecule into halves that are mirror images of each other. As you can see this place, that plane of symmetry is the line that divides from this carbon the one compound into two halves of the same mirror image. So that's what we call plane of symmetry. And I'll tell you about center of symmetry. You can see the center of symmetry is any point in space such that any group of on the molecule can be reflected back through the point an equal distance but opposite direction, and an equivalent group is found. This is relatively rare in organic chemistry. So center of symmetry is relatively rare. This is like, for example, from the middle, or like the sum is like center of symmetry is like equidistance. So everything is same distance from the middle. All the atoms groups, the atoms, everything, they have the same distance from the middle. So the middle is the center of symmetry. Then an axis of symmetry is an imaginary axis around which, by rotating through a minimum angle of rotation, 360 degrees, the original compound is obtained. As you can see, an axis of symmetry, you can see the first compound, the methyl group and the hydrogen group, and the ethyl group and hydrogen group, then one side in this place. Then after rotating for 180 degrees, it changes sides. Then after rotating for another 180 degrees, which make it 360 degrees, it rotates to the normal place it came before. So that's how axis of symmetry looks like. Then talk about optical isomerism. The stereoisomers, which resembles each other in chemical properties and most of the physical properties, but differ only in their behavior towards plane polarized light, are called optical isomers. And this phenomenon is called optical isomerism. It is, yes, ma'am. PPT. I've been changing the slide, ma'am.